Well, in this lecture, we study chain rule. So topic of this lecture is chain rule. So topic is chain rule. So, so we state and prove chain rule. So first we state the theorem. So this is chain rule. So it says that if f and g are functions, f is from Rn to Rm and g is from Rm to Rk, so if these are differentiable at the point at a belongs to Rm. So f is differentiable at a belongs to Rn. So this is n, and g is differentiable at f of a, that is equal to b. So this is n. F is differentiable at a belongs to Rn, and g is differentiable at b, which is equal to f of a, and f of a that belongs to Rm. So respectively. Then the composite function g composed with f. So g composed with f, that is function from Rn to Rm. Then composition of f and g, this is also differentiable at a belongs to Rn. This is differentiable at the point a belongs to Rn. Moreover, so furthermore, the derivative of g composed with f can be written as, so the derivative of g composed with f at the point a is equal to, so in terms of derivatives of f and g, so derivative of g at the point b, where b is equal to f of a, composed with derivative of, so derivative of f at the point a. Okay, so this is the theorem statement. So so suppose this is Rn, so here we have Rn to Rm. This is the function f, and a maps to f of a, which is equal to b. And here we have the function g from Rm to Rk. Then d of f, so derivative of f at the point a. So what is that? That is linear function from, so that is linear function from Rn to Rm, and derivative of g, so that is linear function of, so derivative of g at the point b, so that is linear function from, linear transformation from Rm to Rk. And the composition of derivative of f with derivative of g at the points a and b respectively. So this is the composition dg at B composed with derivative of f at the point A. Okay, so and here we have the composition function that is from Rn to Rk. So this is the composition function G composed with f. G composed with f. Okay, so here we have a commutative diagram that is G composed with f that is equal to so this takes Rn to Rk. So here also we have commutative diagram. So if this diagram is commutative, so if first diagram is commutative, then second diagram is also commutative. Okay, so now we prove chain rule. Proof of the theorem. So f is a function from Rn to Rm that so that is differentiable at the point A. So df at the point A that is the derivative of f at the point A. This is linear from Rn to Rm. So this is linear. So we denote this linear transformation derivative of f at A by Tf. So Tf. So we denote this linear transformation derivative of f at A by T of T sub A. So this, and G is from Rm to Rk, and its derivative dg at B, where B is equal to f of A. So derivative of G at B, that is linear from Rm to Rk. So we denote this linear transformation by Tg. So we define Tg equal to derivative of G at B, where f of A equal to B belongs to R. Now we define phi of x that is equal to f of x minus f of A minus T sub f acting on x minus A. And this is we label this equation by equation number 1, and then we define psi of x. Similarly, this is equal to g of. So here in equation number 1, x belongs to Rn, and next we define psi of y that is equal to, so psi of y that is equal to g of y minus g of b. So this is g of b minus t sub g y minus b. This is equation number 2, and here y belongs to Rm, and then we define rho of x. This is equal to g composed with f acting on x minus g composed with f acting on A minus t g composed with t f acting on x minus A, and this is equation number 3. Now we use the fact, so use our assumption that f is differentiable at the point A. So because so f is differentiable at the point x equal to A. So by the definition of derivative, so by definition of derivative, we have limit x tends to A, norm of phi of x, norm of phi of x over norm of x minus A. So this is equal to 0. So by definition of derivative, by definition of differentiation. So by definition of differentiation, we have limit x tends to A, norm of phi x over so norm of x minus A, that is equal to 0. So by definition of derivative, we have this equation, and we denote this equation by equation number 4. So this is equation number 4, and G is differentiable at y equal to B. So from G we have limit y tends to B, psi of y, norm of psi y over norm of y minus B. This is equal to 0, and we label this equation by equation number 5. So now what to show? To show that limit x tends to A, rho of x, norm of rho x over norm of x minus A, and this is equal to 0. So this is what we need to show. Now what is rho x? Now rho of x, this is equal to G composite F acting on x minus G composite F acting on A minus T G composite T F acting on x minus A. And from equation number 1, so from equation number 1, T sub F acting on x minus A, so this is equal to basically f of x minus f of A minus phi of x. So in this equation we replace, so this is equal to G composite F acting on x minus, so f of A this is equal to B, so G of B, and minus T G of, so we replace this quantity T sub F acting on x minus A by f of x minus f of A minus phi of x. So this is by equation 1. And now this is equal to G of f of x minus G of B minus T sub G acting on f of x minus, so f of A equal to B, so minus B, and plus T G acting on phi of x. So here we have applied the property of a linear transformation. TG is linear transformation. Okay. So from here, this is equal to psi of f of x, and plus, so this part is psi of f of x and plus t g of Vx. Now, so this implies rho of x, so norm of rho x over norm of x minus a. So this is less or equal to, by triangle inequality, so this is less or equal to norm of psi of fx over norm of x minus a plus tg. So norm of tg of phi of x, so norm of this over norm of x minus a. And this implies limit x tends to a, norm of rho x over norm of x minus a less or equal to limit x tends to a, norm of psi of fx, norm of psi of f of x over norm of x minus a plus limit x tends to a, norm of tg phi of x over norm of x minus a. So now, so basically this is we need to show. So from this inequality, now it's suffices to show this individual limit is I mean, this is equal to 0 and this is also equal to 0. That is, so now it suffices to show the following equations. Limit x tends to a, norm of psi of f of x over norm of x minus a, this is equal to 0, and we label this equation 6, and limit x tends to a, so this is tg, so norm of tg acting on phi x, so norm of tg acting on phi of x over norm of x minus a, so this is equal to 0. So if we can show equation 6 and 7 holds true, then that will imply limit x tends to a, norm of rho x over norm of x minus a, that is equal to 0. So that is what we want to show. So now we prove equation 6 and 7. So first let us prove equation 7. So proof of equation 7. Well, so Tg, this is linear transformation, so acting on phi of x, and therefore there exists some m such that this quantity is less or equal to m times norm of phi of x. Okay, so we are using the fact, so we are using the fact if t is linear from Rn to Rm, so if this is linear, then there exists some m in positive set of positive reals such that norm of Tx is less or equal to m times norm of x. So here, so on the left hand side here, norm is norm in Euclidean norm in Rm, and here Euclidean, this is norm in Euclidean norm in Rn. Okay, this happens for every x belongs to Rn. So here we are using this fact. To get norm of Tg acting on phi of x less or equal to m times norm of phi of x. So for some m belongs to r greater than 0, and therefore, so this implies norm of Tg phi of x, so norm of this over norm of x minus a, limit x tends to a. So this is so well. First look at this quantity. Then we put then we'll put norm. So then we'll put the limit. So this is less or equal to. So the numerator is less or equal to m times phi of x, norm of phi of x, and divided by x minus a, norm of x minus a. And then we put limit x tends to a, here limit x tends to a, and the right hand side, so this is equal to m times limit x tends to a times, so this is the function is norm of phi of x over norm of x minus a, and this is equal to 0 by equation number 4. So here we have equation number 4. So equation number 4, this says that limit x tends to a, norm of phi of x over norm of x minus a, that is equal to 0. So using equation number 4, so here we have this is equal to 0, and this implies, so this is non-negative, so this must be 0, and this implies equation 7. So this is the proof of equation 7. Now we prove equation 6. So now we prove equation 6. So here we use epsilon delta definition. So first we apply epsilon delta definition on equation number 5. So equation number 5 is here. So let me write equation number 5 over here. So equation number 5, limit y tends to b, psi of y, norm of psi of y over y minus b, norm of y minus b, this is equal to 0. So from here we have, for given epsilon greater than 0, there exists some delta greater than 0 such that the functional value, so psi of y, so this is non-negative, so norm of psi y over y minus b. So this quantity is less than epsilon for all y not equal to b belongs to Rm with y minus b, so having norm less than delta, and this implies norm of psi of y, this is less than epsilon times norm of y minus b. This happens for all y not equal to b. So here, so y might be equal to b also. So we don't need condition for this equation. We don't need condition y not equal to b. So we have for all y minus b having norm less than delta, y belongs to so y belongs to R, Rm, and so if we remove the condition y not equal to, so y not equal to b, then we have to put a less or equal to. Now, well, so replace y by f of x, and so this implies norm of psi acting on f of x. Norm, this is less or equal to epsilon times f of x minus f of a. Norm of f of x minus f of a. So this happens for f of x minus f of a having norm less than delta. So, well, now note that f is a continuous function, so f is differentiable function at the point a, and this implies f is continuous at the point a. So using the property of continuity of f at the point a, so we have for this delta greater than 0, so by continuity of f at a, so for delta greater than 0, there exists some delta prime greater than 0 small enough such that f of x minus f of a, so norm of this is less than delta whenever x minus a has norm less than delta prime. So this is from continuity of the function f at the point a. So, well, now for such a delta prime, so for such a delta prime, what we have is psi of fx. So now we put the things together to get, so for such delta prime greater than 0, so we have psi of fx. This is less than epsilon times norm of f of x minus f of a. So we can put less or equal to, and so this is equal to, so epsilon times norm of, so what is f of x minus f of a, and that is by equation number 1. So this is less than, so this is equal to phi of x minus tf acting on x minus a. So norm of this, and this is, so this implies norm of psi of f of x. This is less or equal to epsilon times. So here we use triangle inequality. So this is basically plus sign. So f of x minus f of a equal to phi of x plus tf acting on x minus a. So now here we use triangle inequality in this equation. So this is less or equal to epsilon times phi of x norm of phi of x plus epsilon times norm of tf acting on x minus a. So norm of this. Now this implies psi of f of x norm of this over norm of x minus a. So all this happens when x minus a so has norm less than delta prime. Okay, so this less or equal to epsilon times norm of phi of x over x minus a plus epsilon times norm of t f acting on x minus a over norm of x minus a, and this is less or equal to epsilon times phi of x norm of phi of x over norm of x minus a plus epsilon times some m. So previously we have used some m. So what is m? So t. So here we have used for the linear transformation tg we have used m. So let me denote it by mg, and this is also mg. Okay, so here we use m. So for the linear transformation tf we use mf. So epsilon times mf times norm of x minus a and divide by norm of x minus a. So that will cancel out. So we have epsilon times m of f. So for some mf belongs to r greater than 0. Now and equation number 4 implies that limit x tends to a. This is so limit x tends to a norm of phi of x over norm of x minus a, that is equal to 0. So and epsilon is arbitrary. So epsilon is arbitrarily chosen positive number. So this implies limit x tends to a norm of psi of x over x minus a norm of x minus a. So this is equal to 0. So this is equation 6. So this is the proof of equation 6. So now this completes the proof of chain rule. So we stop here.